Here are solutions to homework set number 4 for ECE 463-663 Modern Control. In this homework set, we look at coming up with the dynamics for a ball and beam system, current pendulum system, and a gantry system. Now we'll be using these solutions for the rest of the semester. These are the dynamic models that we'll be trying to control. The first one looks at a current pendulum system. I've got a cart of 1.5 kilograms, a beam length of 1.5 meters, and a ball on top, mass of 3 kilograms. Force on the base. What are the dynamics? To do this, we'll use the LaGrangian formulation. First, find the kinetic energy, potential energy, then find the dynamics. So starting out, for the cart, I've got its position is just x and 0. The derivative is x dot 0. Potential energy is mgy, 0. Kinetic energy is 1/2 mv squared. Okay, that was easy. The second one, the second mass, its position is x plus 1.5 sine theta. Y position is 1.5 cosine theta. Take the derivative. Derivative of x is x dot. Derivative of sine theta is cosine theta, theta dot. Likewise, y dot. Potential energy is mgy. Kinetic energy, 1/2 mv squared. Substitute, do some algebra. I wind up with the kinetic energy. Lagrangian's kinetic energy minus potential energy. So here's the first mass, second mass, potential energy. There's Lagrangian. Simplifying, here's what I get. Now the force on it would be the full derivative of the partial derivative with respect to x dot minus the partial derivative with respect to x. This is what you could expect on the first test, something like this. Here's Lagrangian, find the force. To do that, I find the partial derivative with respect to x dot. So here's an x dot, that becomes 4.5 x dot. No x dots, ignore. There's an x dot. 4.5 theta dot cosine theta, no x dots, ignore. Minus the partial with respect to x. There are no x's, so 0. Now take the full derivative. The full derivative is derivative with respect to x dot is x double prime. Chain rule. Derivative with respect to theta dot is theta double prime. Derivative with respect to the cosine theta. Derivative of cosine theta is minus sine theta, theta dot. Times another theta dot gives you theta dot squared. So there's the force. The torque is full derivative of the partial with respect to theta dot minus the partial with respect to theta. Partial with respect to theta dot, no theta dots. Here's a theta dot. There's a theta dot. Again, theta is different than theta dot. Ignore. Minus the partial with respect to theta. No thetas, no thetas. Here's a theta. Cosine becomes minus sine theta. And here's a theta. Now take the full derivative. Gives you theta double prime, x double prime, and chain rule, minus sine theta, theta dot. Conveniently, these cancel. So there's the torque. So this is the dynamics for a cart and pendulum system. To animate it, I would pull these out. I would have acceleration for x and theta. Here's my mass matrix. Here's the force and torque. Bring these terms left. There's the Coriolis and gravity forces. To solve, I would take the inverse of that matrix times these. I get the acceleration. Integrate once, I get position. Integrate twice, I get velocity. And that's really what the animation does. Going over here, this is the animation for the, let's do the gantry system. I get the dynamics. There's the mass matrix. There's everybody else. My torque matrix, or force matrix. The inverse of the mass matrix times this is the acceleration. Then to simulate it, once I get the acceleration, integrate, I get velocity, integrate again, I get position, or in state space form. This has position, angle, velocity, angular velocity, that's the states. Integrate, I get the positions, draw it, simulate it, and here's what she looks like. I can find the screen. Well, if I run that, let's have no input. Here's the dynamics when gravity, let's do that again, is pulling down. If I flip the direction of gravity, it's unstable. Okay, to see that, to come up with a linearized model, let's linearize about 0. So cosine theta becomes 1, sine theta becomes theta, theta dot squared is small, so ignore it. Invert, I get these dynamics. Put that in state space form. So x double prime is minus times g, 3.6 times x dot. Theta double prime is plus 3.6 times theta, the second state times theta. Find the eigenvalues, and when gravity is pulling it down, it's unstable. That's the pendulum pointing up. Change the sign of gravity, and it becomes J1.89. So that's what we saw here, unstable. If I flip gravity, that's oscillating at 1.89 radians per second. That's the Cartan pendulum system. Ball and beam system. Here's a beam. I have a torque spinning it around. On top of it, there's a ball rolling back and forth. Find the dynamics. Again, same procedure. Find the position of the ball. Take the derivative. Assuming a solid sphere, that's the rotational inertia of the ball. That's the rotational inertia of the beam. No, correction. That's the rotational inertia of a solid sphere. Substituting, I got the inertia of the beam. No, try again. This is the ball as it rolls. The rotational velocity is related to the radius and how fast it's moving. This is how the ball's rotational inertia affects it if it's a solid sphere. Potential energy, total kinetic energy of the beam, the translational kinetic energy of the ball, the rotational energy of the ball. Put it all together, there's kinetic energy. Okay, so when I'm done, I get the Lagrangian, the kinetic energy minus potential energy. That's what I'm shooting for. Now to get the dynamics, the force on the ball is the full derivative, the partial derivative with respect to r dot minus partial derivative with respect to r. So here's an r dot, that's it. For the r's, here's an r, there's an r. Take the full derivative, this is the force on the ball. Repeating for the angle, that gives you the torque on the beam, partial with respect to theta dot, partial with respect to theta dot, and that's it. Partial with respect to theta, here's a theta. Take the full derivative, first term, chain rule, theta dot, r dot. Derivative of r squared is 2r, r dot. Put that in matrix form. This is what's used in animation. So over here, when I get the beam dynamics, this is the mass matrix. Here's everybody else in the torque. The inverse of mass times that gives acceleration. If a linear is about 1 meter, take the inverse, I get these dynamics. Find the eigenvalues. Eigenvalues are plus minus j 2.6, plus minus 2.6. So in this case, if I animate it, let's do a beam with no input. Give some initial condition. It's unstable. It just rolls off the edge. So that's homework set number 4 for 463. Kind of painful. But the thing to note is with Lagrangian formulation, I can actually find the dynamics of fairly complicated systems. Ain't fun, but you can do it. From this point onward, we'll be using these dynamics to try to control the Cartan pendulum, gantry system, ball and beam system. That's homework set 4 for 463.